In this video, we are continuing section 6.4, and we're going to talk about irrational numbers. Before we talk about irrational numbers, let's talk about rational numbers, which we talked about at the start of this chapter. So, rational numbers. I'd love it if you actually went and looked it up if you can't remember. It's good practice for our brain to help us remember, even though I'm about to write it down. But a rational number is a number that can be written as a fraction. We talked about how integers are all rational numbers because any whole number can be written as a fraction if you put it over one. Finite decimals are rational numbers because you can write them as fractions based on the place value. We showed a technique for how to take a repeated decimal and write it as a fraction. So those are rational numbers. Basically, though, now, if there's anything else that can't be written as a fraction, that's an irrational number. And that's how I'm going to define an irrational number. An irrational number is a number that cannot be written as a fraction. Now, I talked about irrational numbers briefly when I first was introducing rational numbers, and I kind of defined them to be numbers that go on forever but never repeat. So these are numbers, that go on forever but never repeat. And of course, I referred to the famous example, the most famous irrational number, pi. Pi is a number that goes on forever and never repeats. But we actually just found another irrational number in the last video, and that is the square root of 2. The square root of 2 is also an irrational number. When we plugged into the calculator, we got a gross decimal, which I didn't really talk about. But the truth is that gross decimal doesn't repeat. And that means it's an irrational number. In fact, you've seen irrational numbers many times in your life without really realizing it. These decimals that come off the calculator that are gross and just kind of go on forever, and or you don't see the end of them and they don't repeat, those are all irrational numbers. So let's look at a more detailed example where they have us doing some classifying. So what numbers, or I should say which numbers, are irrational? It's a weird looking eye. Let's fix it. Irrational. Okay, so let me give you a list of numbers and we'll decide which ones are irrational. Okay. Oops. Dot, dot, dot. Okay, so that's 0 point. And then the next number is 0 point. Okay, there we go. 5 different numbers. I want you to kind of consider each one. If you need to pause the video, I'd love it if you tried to answer it. Go for it. The first number definitely has a pattern. You can kind of see it. The fact that it's repeating the 0, 0, 6 tells me that's a rational number. So here, I'll go ahead and I'll indicate rational, even though they really are after us indicating irrational. Okay, part B, Let's see. It kind of has a pattern, right? But unfortunately, it's not a repeating pattern. I mean, I can indicate what the next part of this decimal is going to be because it's indicating more and more ones, but it's not repeating. So because it's not repeating, that makes this one irrational. Let's see, part C doesn't have the dot, 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 and that actually matters. That means it's a finite decimal. The minute it's a finite decimal, it's a rational number because I can look at the last place value and write it as a fraction, right? So on this one, let's see, that's tenths, hundredths, thousandths, 10,000s, 100,000s. So I'd put 1,011 over 100,000. That's how we could write that as a fraction, makes it rational. Okay. Let's see. The next one, the square root of 81. Oh, well, that one is rational because I know what the square root of 81 is. It's 9. And that can be written as 9 over 1. Square root of 10, however, is not a perfect square, and therefore it's irrational. So like 2, if I plugged into the calculator, it's going to go on forever with no repeating. So there we go. There's 2 numbers that are irrational. Okay, now they kind of take this a step further then, and they kind of look at the simplifying we did with radicals or square roots, square roots, and kind of talked about how that's able for us to look at whether things are rational or irrational. So let's classify as rational or irrational. So this one, they actually do want us to list them. If it's rational, evaluate it. In other words, if it's possible to simplify it, simplify it. So let me give you an example. 3 times the square root of 24. Okay, so I'm going to take a moment and try to ration or simplify the square root of 24. Let's see, 4 goes into there. So there's our perfect square. We can break it up as 4 and 6. So we can write this as 3. Since that's next to the radical, that means multiplication. So 3 times 2, that's the square root of 4. I don't know why I wouldn't just go underneath. I'm sorry. Okay. 3 times 2 times the square root of 6. There we go. And that's going to be 6 square root 6. But the 6 is not rational, so this is irrational. Okay. Part B. Let's try another one here. Let's do 5 square root 36. Okay, now that one, 36, that's a perfect square. And again, since it's 5 is times that or outside it like that, we can assume it's a times. So 5 times 6, that's 30. So they want that included as part of the answer. And this would be rational. Actually, now that I'm thinking about it, then I probably didn't need to simplify number part A there, because they only told me I need to worry about the rational ones. Okay. All right. That's fine. We'll be wiser now. Here, let's look at part C. Part C, 14 plus radical or square root 14. Sorry, I do kind of use the word radical and square root interchangeably. So I apologize. I'm trying to use the word square root because that's what we've been talking about. Can't take the square root of 14. That's not a perfect square. So this one is irrational. I'm not going to try to do any simplifying. I can't really do any simplifying, but we won't even talk about it. That's probably how I should have approached part A. D, square root of 81 plus the square, or sorry, just plus 18. Okay. That one we could do some simplifying because square root of 81 is 9. 9 plus 18, that's 27. So there we go. It's rational. Just kind of squeeze it right next to it. And there we go. So they do have you kind of work with the square roots and simplifying them like how we talked about in the previous video. And then they also do some multiplying. So here we'll call it part E. So let's say we have the square root of 8 times the square root of 6. See, now in this case, you do need to multiply first. So we're going to use the fact that because they're both under radicals, we're going to go the reverse direction now. We're going to multiply 8 and 6, which is 48. That's not a perfect square. 49 is, but that's not. So this one is irrational. I could simplify it if I wanted to, just so you know, okay? That would break up as 16 and 3, just so you're aware of it. If I wanted to just take it one step further, which means it would be 4 radical 3, or 4 square root 3. Part F, this will be the square root of 12 times the square root of 3. That one, when we multiply, gives us the square root of 36, which we know is 6. So it's rational. And there we go. So yeah, they have us kind of play with the square roots a little bit since we talked about that in the last section. All right, and now this really leads us into real numbers. Before I do that, though, I'm going to take one moment and discuss. I don't even know if I put it in the homework, but I do want to just mention it. There are higher radicals, higher roots, okay? Like, for instance, you could look at what's called the cube root. The cube root, we put a 3 on it instead, is now you're saying what number times itself 3 times gives us A, right? So this would equal B if B cubed equals A. Okay, so here, just do a quick example of a basic cube root, one that's not too complicated. The cube root of 8. So what number times itself 3 times gives us 8? I hope you know. It's 2, right? 2 times 2 times 2. That gives us 8. Okay, so cube root. And it's possible to do a fourth root, which typically at this point they start calling them higher roots or nth roots, which they use an n then to indicate. Okay. So like we typically stick with pretty small numbers for these. So like, let's see, a fourth root, let's do the fourth root of 81. The fourth root of 81 is 3 because 3 times 3 times 3 times 3. I hope we see it. That's 9 times 9, which is 81. All right. There you go. Just a quick little glance. There are higher roots. I don't believe I really assigned any of those, so I don't want you to get too hung up on them. But it is possible to go even further and look at perfect cubes and perfect fourths and kind of talk about higher roots. Okay. Real numbers, though. That's really where we're trying to head. And the real numbers are all numbers that are both irrational and rational numbers. Real numbers are all rational and irrational numbers. Now, when I introduced rational numbers, I drew a picture of the sets of numbers and kind of talked about the sets of numbers, but I just want to review that. And I want to give some labels because the book gives some labels to it as well. Now, the book doesn't define the natural numbers, but because I mentioned it, I'm going to go ahead and show you. They use this kind of funky capital N with a double bar, okay, to represent it. That's how we kind of draw it out on the paper. Some of the old math textbooks use this notation. Most new math textbooks use like a bold capitalization, but that's kind of harder for us to indicate on notes. So I like the double bar notation because it kind of gives it a special look so we know, or they'll use italicizing. So we know that it's a special notation. So this is representing the natural numbers, also known as the counting numbers, which I listed previously. So I'm not going to relist those numbers, but I'll say it. It's 1, 2, 3, 4, and so forth. Then we have the whole numbers, which uses a fun W. The whole numbers pick up at 0, 1, 2, 3, 4, and go on forever. Then the integers, they use a Z to represent the integers. The reason is the I is going to be taken for the irrational numbers. So they give a Z to the integers, and I believe it had something to do with like the Latin name for integers. Integers are positive and negative whole numbers. Rational numbers, they call Q, and they do that because the R is taken for real numbers. But they use Q for quotient. So these are rational numbers, and it's kind of a alluding to the fact that we're talking about fractions, quotient, fractions. I is irrational numbers. And then finally, R is the real numbers. And there we go. Now, the book kind of draws a similar picture to what I did, but a little bit altered. And I did want to show it to you because I also included a set notation. Here, I'm going to just mention what page it's on if you want to go look at it. But I'm going to draw it here, 389, just so you know. So this is from page 389. Okay, so they start with big circle, which is the real numbers. I'm just going to use the symbols we just bothered writing down to make our life a little bit easier. Okay, then they divide the real numbers in half, and they have the irrational numbers and the rational numbers. Within the rational numbers, we have the integers and the whole numbers. And technically, if we wanted to, inside the whole numbers, we could draw the natural numbers. They don't bother with that. They didn't even introduce the natural numbers in this particular drawing. So what they do show, though, is this idea of subset notation from back when we talked about sets. And they say that the whole numbers are a subset of the integers, which are a subset of the rational numbers, which are a subset of the real numbers. So they kind of go back to that old notation that we talked about when we talked about sets to kind of also tie it together to when we discussed that. They do have you do some identifications, numbers that are integers versus a whole number versus a rational number versus a real number versus, irrational. Like they have some categorizations of that, but we kind of already did that when we talked about the difference between rational versus irrational. Okay, so I just want to kind of move into the properties of real numbers. And really, what I'm interested in doing is summing up what we've discussed, all the properties, and I know we've talked about them briefly before. We're just going to briefly sum them up again. That's funny. Let A, B, and C be real numbers. So every time I write one of them down, I'm referring to a real number, a number that is either rational or irrational, doesn't matter. The real numbers have the property called closure. Now, I don't remember if I've talked about it, but closure is the idea that when you add two real numbers or multiply two real numbers, you will get a real number as an answer. So when you add two real numbers like A plus B, that is a real number. And here I'm going to use the number symbol. Or when you multiply, that is a real number. So whenever you add them, whenever you multiply them, you always get a real number. I know that doesn't sound very exciting, but there are number systems that exist that when you add them or something, they may not give you the number system that you're working with. So we have different things to look at in those cases. But with real numbers, nothing weird like that happens to us. We don't all of a sudden see a brand new number system. The commutative property holds over real numbers. Commutative property is when you could switch the order. So it works for both addition. We can add and say that A plus B is the same thing as B plus A. And multiplication. A times B is the same thing as B times A. We have the associative property. The associative property is when you can reorder the priority. given on order of operations. So if you have A plus B plus C, where B plus C is given the priority because it's in parentheses, you, because it's all addition, could go ahead and add the A and B first and then add C. We've definitely seen these before. I'm just reiterating them for all real numbers. Every number we have worked with at this point, even the irrational numbers, work this way. Multiplication, that's A times B times C is the same thing as A times B times C. Cool. Then we have identities. Identities are the magic numbers that don't affect us when we add or multiply. For addition, the identity is 0. Why? Whenever you add 0, it doesn't do anything. For multiplication, the identity is 1. Why? Whenever you multiply by 1, it doesn't do anything. So 1 and 0 are special, and they are actually called identities. Inverses are when you look at numbers that add up to the identity or multiply to the identity. So if you're looking in general for addition, two numbers are going to add up to 0. That means that they have to be opposite signs. So A and negative A are always going to add up to 0, the identity. For multiplication, in order to give us 1, it has to be a fraction, or what we call the reciprocal. So a number times its reciprocal is always going to give us 1, the identity. And then last, distribution still holds. The distributive property. The distributive property combines multiplication and addition. If you have A times B plus C, that is A times B plus A times C. And all of these properties, regardless of irrational or rational, all work all the time and never do anything weird. We always will get back real numbers. And there you go, real numbers.